Okay, so thanks for coming to my talk. The talk is on temporal concept localization on videos, specifically on a data set called YouTube 8M. So before I begin, this is joint effort from a Layer 6 team. So it includes Jeremy Ma, Maxim Vokovs, Ilya Stanovic, Guangwei Yu, and myself. All right, so let's first get into the task at hand. So what is recognition and localization? So action recognition involves basically identifying all the action classes that occur in a video sequence. So a video is obviously quite long. There can be multiple actions that take place. So this is typically a multi-class classification problem. And action localization is a little more specific. So action localization involves finding the boundaries of where the actions occur and what actions occur within those boundaries. So as an example in this picture, we have the boundary of alpine skiing starting from a frame A to frame B, and we need to identify where these boundaries are and what actions that happen in these boundaries. So I was talking about actions, but concepts in the dataset, YouTube 8M dataset, is a lot more general. So it can be like it can be a lot more high level. So it can be actions like skateboarding, dancing, but it can also be more general entities such as acoustic guitar, wedding, and so on. So I just put a picture of like a bunch of classes that are actually in the dataset. So you can see things like music video, concert, dance. So they're very general. So that is what we're trying to identify. So before I get into more details, let's take a look at the numbers of the dataset. So the dataset has 6.1 million videos. This is by far the largest video dataset, and it has over 3,000 classes or concepts. And since it's a multi-class problem, each video has approximately 3 labels, 3 concepts. And also, like, the video is broken down logically into segments of 5 seconds. So these are called segments. So before I get into details, like, I want to make sure that you understand between video level labels and segment level labels. Video level labels are labels given to the entire video, whereas segment level labels are labels given specifically within the segment of length 5 seconds. Also in the dataset, the frames are sampled at 1 hertz. So basically, for every second, we have 1 image frame that is sampled. All right, so getting into a little more details, out of the 6.1 million images, videos, we have about 47,000, which is a tiny fraction of them, having segment level labels. So these are both positive and negative labels. So positive labels are basically labels where the actions actually occur in that segment, and negative labels are where the actions don't occur in that segment, and we have a good balance of these, approximately 50-50. So that's what we're dealing with. So now the task of localization is basically to localize actions within segments, or concepts within segments. So we need to classify each of these segments into a bunch of concepts. So that is the task at hand. So the evaluation that that I'll be talking about, all the models are evaluated on mean average precision at 100,000. So all the results that I'll be showing you later on will be on this metric. So if you guys are not familiar with MAP, so MAP is calculated by basically retrieving the top 100. So MAP at 100,000 is calculated by retrieving the top 100,000 candidate segments for each class, calculating the average precision for that class, and then taking a mean across all classes. So that's how we get MAP. All right, so let's get into the fun stuff. So how is feature extraction done on the data set? So preliminary feature extraction is done as follows. So we take each image frame from the video and pass it through a publicly available inception network, which is pre-trained on ImageNet. And we cut it off at some point, and then we finally do principal component analysis to reduce the dimensions to 1024. So what this does is it gives a fixed length representation for every image in the video. So now if a video is of n seconds, we have n images, and we can represent this entire video with a n by 1024 matrix. So this forms the input to all the other models that I'll be talking about. So these are the initial representations of the video. All right, so let's talk about concept recognition. So concept recognition, like I told you, is to classify the entire video segment, entire video into a bunch of classes. So some of the popular methods in the literature are LSTMs, transformers, ConNets, and Vlad and Fisher vector-based approaches. Obviously, LSTMs and transformers form a very natural choice for modeling temporal relations. And similarly, Vlad is very common in action recognition literature. So at a very high level, let's go through how we can probably model such a problem. So let's say we have an LSTM. We input the fixed length representation that we get out of ImageNet, and after dimensionality reduction, we unroll the LSTM, get the final hidden layer, and then have a classification head that classifies into all the classes that we are interested in. So then we can train this using a simple n-way binary cross-entropy loss. And it's an n-way loss because we want multi-class labels, right? So let's take a look at Vlad, but again, at a very high level. I'll just gloss over it. So in Vlad, you have a bunch of cluster centroids, and your features that are coming out of Vlad are basically distances from these cluster centroids aggregated. So if you can think of the cluster centroids as holding some high-level information, your feature coming out of Vlad is basically the differences or distances from these cluster centroids. So those form actually very good features, but Vlad is not differentiable because you have a hard assignment. NetVlad tries to replace the hard assignment with a soft assignment and learn the cluster centroids and the parameters of these soft assignments together. But I'll just gloss over it. We can chat about it more if you're interested later. So this is like the high-level overview of any model, actually. You have a bunch of you have an n by 1024 matrix as features that are getting into the model. You have a NetVlad encoding layer. You can replace that with a transformer encoding, a LSTM encoding, or what have you. And you have a final classification head, and these can be trained using n-way binary cross-entropy loss. But until now, we've been looking at recognition as a whole, where we classify the entire video into a bunch of concepts. How do we do localization, right? So the localization involves classifying these segments into classes. But so you can do something similar to what we had done before. Instead of n by 1024, we can pass a phi by 1024, which are the representations of the segment. But the main challenge is that you have only 47,000 videos that have their segments labeled, whereas you have 4 million plus videos in the training data set that have their videos labeled. So it's kind of like a waste to throw away all these 4 million and then just train on like a tiny fraction of 47,000. So what do we do? The idea is pretty simple. We do something like weak supervision and fine-tuning. So the idea here is we first train a network on the video level with the video level auxiliary labels. That's why I call it weak supervision. And then we fine-tune them on the small subset of the data set where we actually have labels for the segments. So the way we do it, let's say in the LSTM's case, is, again, you train this LSTM on the video level labels on, let's say, millions of videos, and then you copy the parameters of the LSTM and the fully connected classification layer to make it predict for each segment. So here, cell 0, cell 1, until cell 5 form the first segment. And then we can train this network by fine-tuning on the small labeled subset of the data set. So first, let's take a look at preliminary results, right? So we can see, so these are all the models that we've tried. If you guys want to really know more details about each of these models, you can talk to me later. But on the whole, you can see that the MAP is pretty good, but not really that, it's not a great score for this task. So let's see how we can make it better. And our best performing model is CCRL, which is cross-class relevance learning. I'll talk about it in a bit. So how do we make this even better, right? So I'll draw parallels from a two-stage object detector. So in a two-stage object detector like faster RCNN, you have the first stage that predicts, which is a region proposal layer, which predicts bounding box proposals, and then the second stage layer, which does further fine-tuning on these bounding box proposals and also does bounding box classification. So the premise here being the first stage should give all possible bounding boxes. So it should be a very high recall model which predicts all possible bounding boxes. And then the second stage can further refine this and make this more precise so the precision can go higher. So can we do something like that for videos, where we have a network that predicts most likely, with a high recall, most likely candidates for each class, and then we can use other models to further refine them further. So that's the idea. So the way we do this is, to motivate this further, let's see why we need to do this, right? So for a given class C, right, let's take a look at the total search space for this class. So there are 2.2 million segments. Those are like these small video clips within larger videos that are present in the test set. So for every class, there are 2.2 contenders that can possibly belong to this class, and that's a very large subset, right? Search space. So how about we use a high recall model to further reduce the search space down? So basically what we want to do is here, the green dots represent all the segments that actually belong to a class, and the red dots, which arguably are a lot more than green, don't belong to that class. So we need to use a model to reduce the search space down, as well as retain all the green dots in its search space. So then we can use another high precision model to further fine tune this. So that's pretty much what we do. So at a very high level, let's say, so we use a state-of-the-art video level classifier from Scully et al. 2018 to classify all the videos to classes. So here we have video 0, video 1 to video 3, and each of the blocks within video represents segments. So for this class, we have the probabilities that this model predicted. So that means that so for video 0, this model thinks that there's a 0.7 chance that this class actually belongs inside this video. So then we can sort them, and then we can take the top top videos. And then all the segments within those videos form contenders or candidates for this class C. So what this does is it reduces the pool of search space down to a much smaller, by a factor of 20 actually in our case. So now we have, for every class, we have a pool of candidate segments that are very likely to actually belong to that class. So now we actually measure the recall for this, and then it's a near perfect recall, 99.7. So that means that we are not actually losing out on much by reducing the search space down, because we have a near perfect recall. So we can see later on that this gives us a 5 to 14% boost in MAP, which is a significant boost. So that is first stage. So first, what we do is, in stage 1, we use a state-of-the-art model to reduce the search space down. Now we can use all the models that I've talked about to predict the class likelihoods on each of these segments coming out from the pool. So I've talked about a bunch of models like COMNETs, LSTMs, transformers, and netflags. These are very common in action recognition literature. And we also have another model called CCRL, which is cross-class relevance learning, and which is our best performing model. So to motivate why we needed this model, I will talk about what happens in like a normal baseline classifier, like the ones in the existing approaches. So you have a segment, which is a small video clip. We extract features of the segment. We pass it through, let's say, a gigantic neural net, and then we have an n-way classifier, right? But when you have data sets that have like thousands of labels, these labels are bound to have some hierarchy and like some structure within them. So because this is like an in-the-wild data set, so to motivate this further, I've plotted a t-SNE plot of the bag of words representation of the classes, and we can see that the classes cluster together. So we can see somewhere up, like there is kayaking, sailboat, and sailing that are clustered together. Similarly, we have some makeup products on the side. So, and there's a very high chance that these classes actually co-occur in the data set because it's a multi-class classification problem. And we want to take advantage of this structure in the classes. But if we want to do this in the traditional approach, we need to design something like a hierarchical loss or some sort of weighting on losses, and this becomes really hard to train in practice, given the fact that this model is gigantic, has many tens of millions of parameters. So what we do is, instead of making a model predict class likelihoods for all the classes, we have a joint model where we take segment features and a class embedding, and then predict a joint class and segment likelihood relevance, right? So this model takes the segment features and a class embedding as a pair, and then predicts the segment class relevance. In the example here, this segment was a clip of someone skiing, and the class embedding is, let's say, skateboarding, and they don't match together, so we would like the model to have a low segment class relevance. But what this really opens up is the opportunity to do arbitrary feature engineering. So now what we can do is we can actually encode how a target class co-occurs with other classes. And we can actually do a lot more feature engineering ourselves. And then we can pass all these features as input and try to predict a joint segment class relevance score. So another example is here. We have the class embedding of alpine skiing, and the segment is actually skiing, and we would want the model to predict a very high segment class relevance. So that is CCRL on like a very high level. If you guys are more interested, you can check our ICCV paper and also chat with me if you're interested in more details. But now let's take a look at the results. So when we take a look at the results, we can see that there is a significant improvement just by using candidate generation on each of these models. So you can see the most improvement came on transformer, where the MAP went from 65.24% to 79.55%. And similarly, all the other models are about 80%, and our best performing model, which is CCRL, is 80.91, which is about 0.6% higher than the next best model. So finally, towards the end, like, how do we ensemble these? We have a bunch of models, and it makes sense to ensemble them to even make the performance go higher. For ensembling, we have a very simple procedure. So basically, we take the model's outputs, like the class likelihoods for each of the model, and then we do a simple averaging. And this is because some models are better on some classes, identifying some classes, and some on others are not. So each of these models complement well together, and then give a better score. We also do one last step for post-processing, where we run a one-dimensional filter of equal weight on the video, so that we incorporate neighborhood information, as well as it has a smoothing effect on the outputs of the class probabilities. So let's take a look at the results. So we stand at we currently have state-of-the-art at 83.292 after ensembling, which is quite comfortable, which is a quite comfortable read, about 0.6% above the next best team. Also, contrasting with our single model performances, we can see that just CCRL alone stands at 4th place, and also like other single models stand around 6th or 7th place. And this is actually a very significant result, because most of these models are gigantic ensembles, like at least 10 ensembles that go in together on all the top 10 teams. So it's great to see that candidate generation just boosts the performance so that even single models stand at the top place. So that's pretty much my talk. Thanks for listening. Also, like, I just wanted to mention that we from Layer 6 AI are actively hiring, so feel free to reach out. Yeah, thanks. And we can open up for some Q&A.
Thanks for the talk. It was very good work. I worked on this problem before, and in literature, when we did literature survey, we found this under the category of strong and weakly labeled problem. I would be interested if you have a paper on this, or if you can tell what paper you refer to for this work.
Oh, for this, like most of the state-of-the-art approaches in action recognition, like NetVLAD, NextVLAD, other approaches that actually lead to the best performance on this data set in the previous year. I'm happy to chat with that after. Okay. Can't think about it
Thank you.
At the current time. Yeah.
Any other questions?
Congratulations on winning the competition. Great work. Can you talk a little bit more about the class labels? I just didn't understand what were the features involved in the class label that you did the...
Class labels here?
Yeah, right there. What is the class label? Is it a video representation? Or is
so
it
you can do a lot of things. Like I talked about, this opens up for like a lot of feature engineering. So you can take the bag of words representation of the class, and also there's a higher level representation for the class called verticals, which is like a higher group, like a hierarchy on these classes. So you can encode them. You can be encoded how the co-occurrence of one class with another, and all these just concatenated, normalized from the embedding for the class.
Could you explain why original algorithm model not influencing too much to end result?
So you want to know like why there is such a big boost?
No, not big boost. So see, you have like 74, it changed to 80.
Right.
76 changed to 80 again.
Yeah.
65 changed to 79. So you sort of have some unification of results, which is not expected actually.
Okay, I can probably give you an intuitive idea of why this happens, because most of these models actually typically fall around 70s, but now from the segment candidate generation process, we have eliminated a lot of them that are unlikely, where most of these actually were failing. So once we eliminated the candidates that were not surely belonging to one class, we got a free boost on all these models.
Sorry, just quick clarification. So do you mean that you eliminated a vulnerability and those models originally had varying degrees of that vulnerability, and that's why they had different scores before and the same score after?
It's not like they have the same score after, but so we have the same candidate generation process for all the models. So the candidate generation process reduces down the search space. So now all the models over here are taking this as input, like for every class, the pool for that class as input. So that's why, since we eliminated all the non-possible ones, and where most of these models were actually failing, we can see that most of these models get pretty similar performance boosts.
Hi, I have a question about the step where you compute a score on the pair of the segment and the label.
Right.
I assume you get a score for all possible class
Pairs.
labels.
This one?
Yeah.
So yeah, I get a score for every segment and class pair.
Okay, and so how do you pick the final set?
So now that you have every segment class pair, let's say you want to compute mean average precision. So you take one class, see its pair with every possible segment, and then take the top X, let's say, candidates that fall after your threshold.
Sorry, fall under what?
So you can take so let's say you were computing score for alpine skiing class.
Yeah.
You would take a pair with alpine skiing and all possible segments.
Yeah.
So you get like 0.9, 0.8, some scores, and then you can sort them and take the top 100,000 actually.
Okay, got it. Thank you.
Yeah.